There's a moment in warfare when the mathematics of destruction become so absurd that they stop making sense to the human mind. A trigger pull, a fraction of a second. And suddenly, the air itself seems to tear apart as thousands of projectiles fill the space where enemies stood moments before. These aren't your grandfather's rifles that required careful aim between shots. These are weapons that redefined what firepower meant. Machines that achieved firing speeds so impossibly high that they changed the very nature of combat. From the beaches of Normandy to the jungles of Vietnam, from experimental labs in Australia to the cockpit of America's most feared ground attack aircraft, engineers pushed the boundaries of physics to create weapons that could spit lead faster than the human ear could distinguish individual shots. They didn't just make guns that fired quickly. They made guns that created walls of metal, rivers of bullets, curtains of destruction that nothing could pass through, and the stories of how and why these weapons came to be reveal as much about human ingenuity as they do about the terrible necessities of war. Number 5. The MG42, Hitler's Buzzsaw. The sound alone was enough to break men. Not the roar of artillery or the whistle of incoming bombs, but something closer, more personal, more terrifying. A ripping noise like canvas being torn, except the canvas was flesh, and the tearing never seemed to stop. Allied soldiers gave it names that left no doubt about what they were facing. Hitler's Buzzsaw, the Bone Saw, the Zipper. The Germans, with characteristic directness, called it the Knochensäge, which translates simply to bone saw because that's exactly what it did. The MG42, introduced to the German military in 1942, represented Nazi Germany's answer to a problem they'd been wrestling with since the First World War. They had the MG34, an excellent machine gun by any standard, accurate and reliable, but it was expensive to produce, requiring precision machining and skilled labour that Germany couldn't spare as the war dragged on. They needed something simpler, something that could be stamped out in factories quickly, something that could arm the millions of soldiers fighting on multiple fronts. But here's where German engineering went beyond mere cost-cutting and into the realm of psychological warfare through pure, overwhelming firepower. The weapon they created could fire between 1,200 and 1,500 rounds per minute. Think about that for a moment. That's 25 bullets every single second. The cyclic rate was so high that the human ear couldn't distinguish individual shots. Instead, what you heard was a continuous buzzing roar, a sound that seemed to vibrate in your chest and promised that stepping into its field of fire meant certain death. The MG42 fired so fast that it created what tacticians call a beaten zone, an area where the density of bullets was so high that survival became a matter of pure chance. The engineering behind this impossible speed was deceptively simple. The MG42 used a roller-delayed blowback mechanism, a design innovation that allowed the weapon to maintain incredibly high rates of fire while remaining relatively light and portable. But this speed came with costs. The barrel would heat up so quickly that gunners had to change it every 150 to 200 rounds during sustained fire. Each gun crew carried multiple spare barrels specifically for this purpose, and they practiced barrel changes until they could perform them in seconds, because those seconds mattered when enemy infantry was advancing across open ground. What made the MG42 truly revolutionary was how it changed German infantry tactics. While American and British doctrine placed the rifleman at the centre of infantry combat, with machine guns supporting rifle squads, the Germans reversed this. The MG42 became the centrepiece of their defensive strategy, with riflemen supporting the machine gun positions. This wasn't just about firepower, it was about creating a weapon so devastating that entire platoons would go to ground when they heard that distinctive buzz, giving German forces precious time to manoeuvre or reinforce positions. American soldiers developed a healthy respect bordering on terror for the MG42. During D-Day at Omaha Beach, a single German soldier named Heinrich Severloh claimed to have fired 13,500 rounds from his MG42, earning himself the grim nickname, the Beast of Omaha. Whether the exact count was accurate or not, the psychological impact was real. The US War Department even produced training films trying to convince soldiers that the MG42's bark was worse than its bite, that American machine guns were superior. The soldiers who faced it knew better. The weapon was so effective that it never truly went away. After the war, West Germany rechambered it for NATO standard ammunition and redesignated it the MG3. That weapon, essentially the same design from 1942, remains in service with over 30 countries today. The MG42's influence extended even further, informing the design of the American M60, the Belgian FN MAG, and countless other post-war machine guns. The Buzzsaw had set a new standard for what machine guns could achieve, and that standard was measured in impossible rates of fire that turned battlefields into meat grinders. Number 4, the M134 Minigun, Vietnam's aerial nightmare. The dense jungle canopy of Vietnam created a unique tactical problem. American helicopters, essential for moving troops and supplies through terrain where roads didn't exist, became slow-moving targets as they descended to landing zones. Enemy fighters, hidden in vegetation so thick you could be 5 feet from someone and never see them, would wait until the helicopters slowed, then unleash devastating fire from AK-47s and rocket-propelled grenades. The single-barrel machine guns mounted on these helicopters couldn't provide adequate suppression. They overheated, they jammed, and most critically, they couldn't put enough lead into the jungle fast enough to keep hidden enemies' heads down. General Electric's solution seemed almost absurdly simple. They took their M61 Vulcan, a 20mm rotary cannon designed for jet fighters, and scaled it down. Instead of 20mm shells, it would fire standard 7.62mm NATO rifle ammunition. Instead of being mounted in the nose of a supersonic fighter, it would be small enough and light enough for helicopter door gunners. And instead of the already impressive firing rate of the Vulcan, they pushed the design even further, creating a weapon that could fire 6,000 rounds per minute without overheating. 6,000 rounds per minute, 100 bullets every single second. The mathematics become almost absurd when you think about sustained fire. In just 10 seconds, a door gunner could empty a 1,000-round ammunition box. The weapon didn't sound like gunfire at all. It produced a continuous roar, a sound that veterans describe as somewhere between a buzzsaw and a massive zipper being pulled open. The Viet Cong and North Vietnamese army soldiers who faced it called it the Dragon, because the muzzle flash and tracer rounds made it look like a beast breathing fire from the sky. The secret to this impossible rate of fire lay in the Gatling principle, updated for the 20th century. Richard Jordan Gatling had invented the hand-cranked rotating barrel gun in the 1860s, but electric motors changed everything. The M134 featured 6 barrels arranged in a circle, each one firing once per rotation. This meant no single barrel had to handle the heat and stress of 6,000 rounds per minute. Each barrel only fired 1,000 rounds per minute, well within the tolerances of modern metallurgy. The electric motor spun the entire assembly, and the result was a weapon that could sustain fire for extended periods without the catastrophic failures that plagued single-barrel designs. The impact on Vietnam operations was immediate and profound. Helicopter crews who had felt vulnerable and exposed suddenly had overwhelming firepower at their disposal. During insertions and extractions, when helicopters were at their most vulnerable, door gunners could literally hose down the jungle, creating a curtain of fire that suppressed enemy positions even when you couldn't see them. The psychological effect was as important as the physical destruction. The sound of a minigun firing became synonymous with American air power, a reminder that despite being hidden in jungle cover, you were facing an enemy with technological superiority that could rain metal from the sky. Between 1964 and the end of the Vietnam War, the United States military acquired approximately 10,000 miniguns. They were mounted on everything from UH-1 Huey transport helicopters to OH-6 CIWS scout helicopters, from AH-1 Cobra gunships to AC-47 spooky fixed-wing gunships. Each platform used the weapon differently, but the principle remained the same: overwhelming firepower delivered through impossible rates of fire. The weapon was so effective that it remains in service today, now manufactured by companies like Dillon Aero with modern improvements that extend barrel life and improve reliability even further. The minigun also revealed something fundamental about modern warfare. It wasn't the most accurate weapon ever created. At 6,000 rounds per minute, precision became secondary to volume. But in jungle warfare, where enemies were concealed and exact targeting was nearly impossible, accuracy mattered less than the ability to saturate an entire area with fire. The minigun represented a shift in thinking about suppressive fire, transforming it from a supporting role into a primary combat function. You didn't need to see the enemy to defeat them. You just needed to fill the space where they might be with so much metal that survival became impossible. Number 3. The GAU-8 Avenger, flying around a gun. Sometimes an aircraft isn't built to carry a gun. Sometimes the gun is so powerful, so massive, so utterly dominant that you have to build an entire aircraft around it. That's the story of the GAU-8 Avenger, the 30mm rotary cannon that forms the beating heart of the A-10 Thunderbolt II, better known as the Warthog. This weapon represents the pinnacle of aircraft-mounted guns, a cannon so powerful that when it fires, it produces enough recoil force to nearly equal the thrust of one of the plane's engines. In 1970, the US Air Force faced a problem. Soviet armour was getting better, heavier, more resistant to conventional anti-tank weapons. They needed an aircraft that could provide close air support to ground troops, something that could destroy tanks and armoured personnel carriers. But more importantly, they needed a gun that could punch through modern tank armour from the air. The specifications they drew up seemed almost impossible. They wanted a 30mm cannon capable of firing up to 4,000 rounds per minute, with enough accuracy to place 80% of its shots within a 40-foot diameter circle from 4,000 feet away, while the aircraft was travelling at several hundred miles per hour. General Electric won the contract, and what they created was an engineering marvel that pushed the boundaries of what aircraft-mounted guns could achieve. The GAU-8 is massive. The complete gun system, including the ammunition drum and feeding mechanism, weighs over 4,000 pounds and is 19 feet long. It's so heavy that the aircraft would tip backwards on its tail if you removed the gun without installing a jack under the rear fuselage. The cannon is mounted slightly off-centre in the aircraft, with the firing barrel aligned with the centerline to manage the tremendous recoil forces. The weapon fires a mix of armour-piercing incendiary rounds and high-explosive incendiary rounds. The armour-piercing rounds contain depleted uranium penetrators that can punch through 69mm of armour at 500 metres. Think about that for a moment. These aren't small bullets. Each complete 30mm cartridge is larger than a beer bottle, and each projectile weighs about 3/4 of a pound. When the GAU-8 fires at its maximum rate of 3,900 rounds per minute, it's throwing nearly 50 pounds of depleted uranium and high explosives downrange every second. The engineering challenges were immense. The muzzle blast was so powerful it could blind the pilot, so engineers had to design special measures to manage the flash. The gun gases, which contain no oxygen, could flow into the wing intakes and choke out the engines, so they had to develop systems to prevent engine flameout during firing. The vibrations were so intense they could damage aircraft systems, requiring special mounting and reinforcement. Even the spent shell casings became a problem. Initially, the Air Force wanted to eject them, but that would have affected the aircraft's centre of gravity unpredictably during combat. Instead, the GAU feeds spent casings back into the ammunition drum. During the Gulf War in 1991, the A-10 and its Avenger cannon proved their worth spectacularly. These aircraft destroyed over 900 Iraqi tanks, around 2,000 other military vehicles, and approximately 1,200 artillery pieces. Pilots described the experience of firing the GAU-8 as like riding a bucking bronco. The aircraft would slow slightly, vibrate intensely, and the distinctive brrrr-t sound became legendary among ground troops, who knew that sound meant help had arrived, and enemy armour was about to become scrap metal. The GAU-8 represents something fundamental about American military engineering philosophy. While other nations focused on missiles and guided munitions for anti-tank work, the United States built an aircraft around a gun so powerful it could destroy tanks with bullets. It's a brute force solution to a complex problem, and it worked precisely because the engineers were willing to push firing rates and projectile power to their absolute limits. The Avenger proved that sometimes the old-fashioned approach of throwing lots of very large bullets very quickly at the enemy remains devastatingly effective. Number 2. Metal Storm, the million-round dream. In the early 1990s, an Australian inventor named Mike O'Dwyer had an idea that seemed to come from science fiction. What if you could eliminate all the moving parts in a gun? What if instead of a mechanical action cycling rounds, you could stack bullets in a barrel like fireworks in a Roman candle and fire them electronically? What if you could achieve firing rates not in the thousands, but in the millions of rounds per minute? The concept wasn't entirely new. Inventors had experimented with superposed loads, multiple projectiles stacked in a single barrel as far back as the 1500s. But they all face the same insurmountable problem. When you fire the first round, the hot gases and pressure from the explosion would ignite the propellant behind the second round before the first bullet had even left the barrel. This would cause catastrophic chain reactions, turning the gun into a pipe bomb. O'Dwyer's breakthrough was figuring out how to prevent this chain reaction through a combination of deforming projectiles that expanded to seal the barrel and electronic ignition that gave precise control over firing sequences. Metal Storm Limited, the company O'Dwyer founded, created a 36-barrel prototype system nicknamed Bertha that achieved something no weapon in history had ever accomplished. In testing, this system fired 180 rounds in less than 1/100th of a second. Do the mathematics. That's a theoretical rate of fire exceeding 1 million rounds per minute. To put that in perspective, an M134 Minigun firing for 2.5 minutes would fire the same number of rounds that Metal Storm could deliver in a single second. The technology worked through electronic ignition of stacked rounds. Each barrel contained multiple projectiles loaded nose to tail with propellant between them. When the system fired, an electronic signal ignited the propellant behind the first projectile. As that round accelerated down the barrel, it created a reactive force that pushed the remaining projectiles backward, causing them to deform and seal against the barrel walls. This seal prevented the hot gases from prematurely igniting the remaining propellant. Subsequent rounds were fired with precisely timed electronic pulses, each ignition occurring just as the previous projectile exited the muzzle. The theoretical applications seemed limitless. Naval close-in weapon systems that could create an impenetrable wall of projectiles against incoming missiles, counter-RPG systems for vehicles that could detect and destroy incoming rockets, automated perimeter defense weapons that could saturate an area with fire. The US Navy showed interest, and in 2007, Metal Storm began delivering systems for evaluation. The Australian military funded research. Defense contractors explored applications. For a brief moment, it seemed like O'Dwyer had revolutionized firearms technology. But Metal Storm faced problems that brilliant engineering couldn't solve. The most fundamental was reloading. Once you fired all the rounds in a barrel, you had to reload the entire barrel assembly. This wasn't like changing a magazine. You essentially had to replace the barrel itself, preloaded with ammunition. The cost was prohibitive. The logistics were complex. And for most military applications, the impossible firing rate was actually counterproductive. You could fire 1 million rounds per minute, but only for a fraction of a second before the weapon was empty. The second problem was practicality. In most combat scenarios, you don't need to fire 1 million rounds per minute. Modern warfare often requires sustained fire, not brief bursts. A conventional machine gun firing 600 rounds per minute can suppress an enemy position for several minutes on a single belt of ammunition. Metal Storm could exhaust its entire load in a heartbeat, and then you'd need to perform a complex, time-consuming reload while under fire. By 2012, Metal Storm Limited had burned through over $115 million and was placed into voluntary administration. The company eventually went bankrupt. The intellectual property was acquired by an Australian defence company called Defentex, which has largely kept the technology dormant. China has reportedly continued development, with recent reports suggesting they've achieved similar firing rates with modified electronic ignition systems. But as of now, Metal Storm remains more proof of concept than practical weapon, a fascinating engineering achievement that couldn't find a real-world application that justified its complexity and cost. The Metal Storm story reveals something important about weapon development. Sometimes achieving the impossible isn't enough. You can create the fastest firing gun in history. You can demonstrate technology that seems like magic, but if it doesn't solve a real military problem better than existing solutions, it remains an engineering curiosity. The 1 million round per minute dream lives on in laboratories and in the collective imagination of weapons enthusiasts. But on the battlefield, slower, more practical designs continue to dominate. Number 1. The Phalanx CIWS, the last line of defense. Picture a supersonic anti-ship missile screaming toward your vessel at twice the speed of sound. It's penetrated every defense layer and is now seconds from impact. There's no time for human reaction, no time for orders. That's when the Phalanx close-in weapon system awakens. In a fraction of a second, radar detects the threat, computers calculate interception, and a white cylindrical mounting swivels and unleashes 4,500 rounds per minute of 20mm tungsten projectiles. No human intervention, no hesitation, just automated destruction. Sailors nicknamed it R2-D2 because the distinctive radar dome makes it look like the Star Wars droid, but there's nothing cute about what happens next. Phalanx doesn't just fire at where the missile is, it tracks both the incoming threat and its own bullet stream simultaneously, making micro adjustments in real time to walk the projectiles into the target. It's like a self-correcting garden hose, except the water is tungsten penetrators travelling at 3,000 feet per second. The development of Phalanx began in the early 70s when the US Navy faced terrifying reality. Soviet anti-ship missiles were getting faster and more numerous. Traditional defences had layers of protection, but what happened when everything else failed? The Navy needed a last-ditch weapon that could respond in seconds without human decision-making, something that could put enough lead in the air to destroy an incoming missile even in the final moments before impact. General Dynamics took the M61 Vulcan cannon from fighter aircraft and built an entire automated weapon system around it. But this wasn't just a gun on a swivel. Phalanx combined search radar, tracking radar, fire control computers, and the 6-barreled Gatling cannon into a single self-contained unit. The system would search for threats automatically, identify hostile targets, calculate firing solutions, engage without human input, assess results, and either continue firing or cease automatically. The entire decision-making process happened faster than human thought. The genius lies in its closed-loop fire control. The system tracks the target with radar, fires a burst, then tracks both the target and the stream of bullets it just fired. If the bullets aren't converging on target, it makes instant corrections and fires again. This happens in milliseconds, with radar and computer working together to guarantee hits on small, fast-moving targets. The rate of fire of 4,500 rounds per minute was carefully calculated, fast enough to create a dense cloud of projectiles with high hit probability, but not so fast that ammunition is exhausted before mission completion. Each Phalanx mounting carries 1,500 rounds, providing about 20 seconds of continuous engagement. Most actual engagements fire around 300 rounds, in short, precise bursts that destroy the threat while conserving ammunition for subsequent attacks. The first prototype was tested in '73, improved, and by '77 exceeded all specifications on USS Bigelow. Production began in '78, and by '80 USS Coral Sea became the first fully equipped ship. Today, Phalanx protects every class of US Navy surface combatant and serves with 24 allied nations. The weapon proved itself in combat during the '80s in the Persian Gulf, successfully engaging anti-ship missiles. But perhaps the most impressive validation came from an unexpected application. The US Army, facing constant rocket and mortar attacks in Iraq and Afghanistan, mounted naval Phalanx systems on trailers and created the CRAM system. The results were extraordinary. CRAM intercepted 70 to 80% of incoming rounds. In 2 years in Iraq, Centurion systems knocked down over 100 rockets and mortar shells aimed at the Green Zone. The weapon designed to shoot down supersonic missiles was now shooting artillery shells out of the sky. What makes Phalanx No. 1 isn't just impressive firepower or sophisticated technology, it's the perfect synthesis of speed, automation, and reliability. Unlike Metal Storm's theoretical millions of rounds per minute that couldn't solve practical problems, Phalanx works reliably in combat. Unlike the MG42 or Minigun requiring human operators, Phalanx functions autonomously, making split-second decisions faster than any human could. Unlike the GAU-8 requiring an entire aircraft built around it, Phalanx is compact and adaptable. This weapon has destroyed real threats in actual combat, evolved across multiple generations while maintaining effectiveness, and proven versatile enough to defend against missiles at sea and mortars on land. It's not the fastest weapon ever built, but it's the fastest weapon that actually works when lives depend on it. 4,500 rounds per minute might seem modest compared to Metal Storm's million-round theoretical rate, but that's precisely the point. Phalanx represents the sweet spot between impossible speed and practical application, between theoretical capability and combat reliability. It's fast enough to create an impenetrable barrier against supersonic threats, sustainable enough to engage multiple targets, reliable enough to trust with automated operation, and proven enough that 24 nations bet their sailors' lives on it every day. That's why it earns the top position, not for achieving the highest numbers, but for achieving the perfect balance that makes those numbers matter on the battlefield. These weapons represent more than just firepower. They represent the outer limits of what engineering can achieve when the driving force is military necessity. Each one pushed past what seemed possible at the time, Whether it was the MG42's roller-delayed mechanism achieving 1,500 rounds per minute in 1942, the minigun's rotating barrels delivering 6,000 rounds per minute in the jungles of Vietnam, the GAU-8's massive 30mm shells fired from a flying platform, or Metal Storm's electronic ignition achieving theoretical rates that seemed like science fiction. The future of rapid-fire weapons likely lies not in pushing firing rates even higher, but in finding the sweet spot between rate of fire, ammunition capacity, reliability, and practical logistics. Modern conflict has shown that precision often matters more than volume, that guided munitions can accomplish what walls of bullets cannot. Yet there will always be scenarios where overwhelming suppressive fire remains essential, where the ability to saturate an area with projectiles provides tactical advantages that no amount of precision can replace. If you found this deep dive into the engineering and history behind these impossible weapons fascinating, make sure to hit that like button and subscribe to Ignis Tempora for more explorations of how human ingenuity pushes the boundaries of what's possible, even in the darkest applications. The story of rapid-fire weapons is ultimately the story of engineers solving seemingly impossible problems, and whether we approve of the applications or not, the solutions they created changed warfare forever.